This is called, much more theatrically, the ultraviolet catastrophe. So, uh, one of the results from classical thermo and StatMech, everything with a temperature emits radiation. This is called blackbody radiation. Um, so you like humans, anything with a non-zero absolute temperature gives off some form of radiation. Um, uh, yeah, so blackbody radiation. And the amount of energy given off by this black body is uh, come on, load. Is all right. So I'm gonna call this the spectral emittance, which I will explain in a bit. Uh, Frequency dependent, as a function of the temperature, is equal to two. Still using nu. F squared kbt over c squared. Where so U of t has units of watts per meter squared. So the spectral emittance is a power emitted per unit surface area. Um, and this kBt is Boltzmann's constant. Right? And so what's important about this equation to note is that this spectral emittance is proportional to, and this is this, instead of alpha, this means proportional to, frequency squared, which means the higher frequency uh, of light you have, the more emittance you get from that frequency. Now this creates an issue because how they derived this black body, how they treated this black body in statistical mechanics is by black body description. They treated it like a cavity. So like a 3D box, right? And they solved for the amount of light that could exist inside this box. Um, and as I said earlier, light obeys the wave equation. It is a wave, which means at the edges you can't have any light, but anywhere in between you can have light, which means you're restricted to standing modes of light. So this tells us that uh, lambda. Wait, no. Yeah, lambda equals. Hang on. Hang on. Which means. Hang on. 2 pi over lambda. L has to equal n pi. So lambda equals 2L over n. No, that's not right. I'm going to describe it in terms of the wave number. K has to equal 2 pi n over L. So, light is a particle. We are getting to that. That is important. We will get to that. But what they discovered first historically is that light is a wave. We will get to that. So, this means that so another consequence of solving the wave equation, again, if you want a refresher on the wave equation, Z's video is a good one. Your solution can have any combination of allowed waves. So n equals 1 to infinity of this sine of 2 pi n x over L x. Which means for any blackbody, you have an infinite number of frequencies. But the spectral emittance of a blackbody is proportional to f squared, which means as f goes to infinity, your spectral emittance and therefore the power, the energy inside this blackbody also goes to infinity. Hence, ultraviolet catastrophe. So this showed that this classical version of this classical interpretation of a blackbody radiation only works at low energies and low frequencies. And so how they solved it was Max Planck. Hang on. I'm out of space. I'm gonna move up here. Why isn't this working? Oh, there it is. There it is. So yeah. So Max Planck gave the solution. Instead, so what he did was instead of treating light as a wave, nope, that does not look right. He said, what if light can only give off energy as integer multiples of hf, where this is now unimaginatively called Planck's constant. And so using this formula for the energy of light instead of the one you get from wave mechanics, you end up getting spectral emittance in this form. You get U of F as a function of temperature, or temperature and frequency, I guess, equals, hang on, lambda, so, hang on, lambda, sorry, the equation I have is in terms of wavelength, not frequency. I'm trying to convert it. Lambda equals C over F, so this becomes over C cubed. All right, 2hf to the 5th over C cubed 1 over exponential of hc over, nope, hf over k bt minus 1, where this exponential is e to the hf over kbt. And how this fixes it, even though this is still in terms of f to the fifth, this term, actually, let me use a different color for this. I'm gonna use red. This term, as f goes to infinity, this goes to 0 much faster than this goes to infinity, which means what you end up getting is, actually, let me pull the graph for it. This will be easier to show. Yeah, this is it. All right. So this formula compared to the one we got from classical StatMech looks like this, where I can't annotate this, but as you can see, this is from Wikipedia. The classical theory, again, and also keep in mind this is in terms of wavelength, not frequency. So higher frequency means lower wavelength. So classical theory blows up to infinity as you get closer to ultraviolet. Meanwhile, what that exponential does in the denominator is, because it goes to 0 much faster than the polynomial f to the fifth, it'll quickly drop off to 0 as you get higher and higher wavelengths. So this means that you get finite energy for a blackbody radiation. That's how they solved the ultraviolet catastrophe. And this left us with an interesting conclusion. Light is a particle because it has discrete. Not only is light this actually didn't tell you light was a particle. All this proved was that light can only exist in quantized energy packets. How this transformed into light as a particle was when Einstein then used this solution and Planck's formula for the energy of this quanta of light to solve another problem arising at that time called the photoelectric effect. And Einstein proved that the photoelectric effect is caused by particle-like interactions with where light has energy equal to this h nu, and that fully cemented the fact that light was also a particle and a wave. The 1900s were a very confusing time. So yeah, that's the ultraviolet catastrophe. And just like how the Michelson-Morley experiment gave rise to special relativity, the ultraviolet catastrophe, because it quantized the energy of light, was one of the things that gave motivation towards quantum theory, quantum mechanics. The other thing that gave rise to quantum mechanics was our understanding of the atom, which I will talk about some other time, because those are also very interesting experiments. But as we showed that light is both a wave and a particle, and that we have no idea how an atom worked at the time, we needed quantum mechanics.